Here are solutions to homework set number 3 for ECE 111. The first problem is solving n equations and unknowns. Now MATLAB is a matrix language. With matrices, it's really easy solving n equations and unknowns. The trick then is to put it into matrix form. So the way matrix works, this is a 2 by 2 matrix times a 2 by 1. When you multiply, the first element is times x, the second element is times y. So what I like doing is, just as a reminder to myself, this first column is times x, the second column is times y. So what this means is that 7x plus 4y equals 5, 9x plus 6y equals minus 2. That's these two equations. So to put two equations and two unknowns into matrix form, you just take the coefficients, sort them, x and y, that'd be this guy right here, and then write out the coefficients. 7 times x, 4 times y is 5. In MATLAB, I can input that. And so to input a, I would do a equals square bracket, that's the start of the matrix, 7 comma 4, semicolon, next row, 9 comma 6, end of matrix, and this is what it shows up, and you can look at it saying, yep, that's correct. The B matrix is start of matrix, 5, next row, minus 2, end of matrix, so there's your B matrix. And the answer is inverse of A times B. Now with matrices, the inner dimension has to match, so A is a 2 by 2, A inverse is a 2 by 2, B is a 2 by 1. B has to be a 2 by 1. Some people put a comma in there by accident, and they wind up with a 5 minus 2, a 1 by 2 matrix. That doesn't make sense. B has to be a 2 by 1 matrix. So when you're done, the inverse of A times B gives you the answer, x and y. So that's not too impressive. You can solve two equations and two unknowns by hand. Let's try three equations, three unknowns. Again, the same procedure. I'm going to create this guy, call it x, y, and z, and it gives a reminder. First column is times x, second column times y, third column times z. The first equation is 4 times x minus 9 times y minus 8 times z is minus 3. That's my first equation. The second equation, minus 6 times x minus 4 times y plus 7 times z is 10, and so on. So again, calling this a and b. To input a into MATLAB, I would do a equals square bracket, start of the matrix, 4 minus 9 minus 8, next row, minus 6 minus 4, 7, next row, 5, I did that wrong, minus 9, 4, end of matrix. And print it out, and you can see right here, I made a mistake. I have to fix that on the solutions. There's b, inverse of a times b is the answer. And it's not quite the right answer because I made a mistake there. 4 by 4. Same procedure. This is going to be a times b times c times d. Let's take the second one. I've got minus 2 times a plus 6 times c minus 6 times d. And I need to throw in that 0. 0 b's. I've got to fill in the whole matrix, so you need the number 0. Is minus 3. That's your AB, A, B. Input that into MATLAB. Print it out, make sure it looks right. Yeah, it looks good. There's B. Inverse of A times B. There's A, B, C, D. So that's n equations and unknowns. That's one of the powers of MATLAB. If I can get a problem into n equations and unknowns, MATLAB can solve. And it really doesn't matter. If it's 20 equations, 20 unknowns, MATLAB can solve it. What's important is get the equations right. What happens if you have more equations than unknowns? That's typically what you have with real data. And there, the solution then is if I have, let's call it b, basis function times my unknowns equals y. If I have more equations than unknowns, then what I do is, like suppose I have 100 equations and 2 unknowns, like one I have, or in this case, 3 unknowns. I can't invert a 100 by 3 matrix. I have 100 data points. what I do is multiply on the left by B transpose. B transpose B is a 3 by 3 matrix. You can usually invert a 3 by 3 matrix, so multiply on the left by B transpose B, and that's what you get. The solution, let's put up here, is my unknown A is the inverse of B transpose B, B transpose Y. That's solving n equations, well, actually, solving for n unknowns when I have more equations than unknowns. That's called least squares. And with that, I can solve all sorts of problems. First problem, let's do a parabolic curve fit for the CO2 levels. Now, the beauty of MATLAB and the internet is you don't have to sit there and type in that data by hand. If you go to Bison Academy, that's bisonacademy.com, go under 111, that's this class. Time passes. And we're on week number 3. Here's your data sets. You can go to the National Oceanic and Atmospheric Administration. These are also data sets uploaded onto Bison Academy. I did that so if the government website goes down, we still have the data. And here's your data. The third column is your year in decimal format. So here's year and month. This is month put together. So the third month is 0.2 of the way through the year. The sixth month, 0.45 through the year. CO2 levels. Just copy this data into MATLAB. Then in MATLAB, I can say data equals square bracket, start a matrix, paste. Paste the data there, end of matrix. All my data is now in MATLAB. Recall with the data, the third column right here was the year. The fourth column was CO2 level. So if I pull up the third column versus fourth column and plot them, that's the data that I get. To do a curve fit, I want to do a parabolic curve fit, so pick the basis to be year squared, year, and 1. And one trick to create a ones matrix is take year to the 0 power. Anything to the 0 power is 1, and that gets the dimensions right as well. So that's my basis function. To find my constants, a, b, and c, I just do the least squares curve fit. Inverse of b transpose b, b transpose times y. In this case, y is the CO2 level. And there's my answer. This is a, b, and c. The weighting times year squared, year, and 1. To see how it looks, plot it. Here's year versus CO2 in blue, year versus the curve fit. That guy right there is my basis function in matrix form. That's this guy, or rewritten as year squared, year, and 1 times a, which is ABC. Another way of writing it, that's an A. In red, plot it, and here's what I get. If you look at it, yeah, it looks like a pretty good curve fit. With that, I can start doing things. When is the CO2 level going to reach 400 parts per million? And I know that answer. I can just go over there and look on the graph. It's about the year 2015. In MATLAB, there is no such thing as function equals 400. So what I can do is rewrite this. Bring the 400 left. I want to find the roots of this polynomial equals 0. There is a function, a roots of a polynomial function. It's called roots. So change the problem. So when is the coefficient of a minus 0, 0, 400 equal to 0? And you get this root in the year 2014.8 will be at 400 parts per million, which I knew because I have the graph. The stretch is when are we going to reach 2,000 parts per million? That's in the year 2288, about 266 years from now, assuming nothing changes. Least squares are pretty generic. You can curve fit any data. So let's have some fun. Let's look at the temperature in Fargo. In this case, the average temperature in May is the 6th column of the data. You can go back to Bison Academy. Here's your data sets, Fargo temperatures. Takes a little bit of time to load. And this is from Hector Airport. Since 1942, these are the monthly averages in Fargo. The first column is year, and the sixth column is May. So do as we did before. I'll just take the data, do left click, copy it, go into MATLAB and say data equals start of matrix, paste the data, end of matrix. First column is year, sixth column is May. Form the basis, I want to have this form of an answer. So my basis is going to be year and 1. So here's year and 1. A is same as before. Inverse of B transpose B, B transpose times Y. In this case, Y is May. Here's my curve fit. Plot it. And I get this data. So there's my straight line curve fit for the data. And you can see that the temperature is going up. If I ask how much, well, this is the coefficient times year and 1. So it goes up by about 0.04 degrees Fahrenheit per year. Over 80 years, it's gone up 3.6 degrees in Fargo. And I can extrapolate. Want to find out how warm it will be in the year 2050. Again, this is the curve fit, y equals ax plus b. A is a of 1, b is a of 2. Plug it in, and I get 59.12 degrees Fahrenheit. So by 2050, I expect to be right about here at 59.12. Problem 6. If you go to the National Oceanic Atmospheric Administration, they have records of the sea ice levels. If you take the minimum sea ice level per year, here's what it looks like. Come up with a linear curve fit for it. So same procedure as before. Go to the data set, copy the data into MATLAB. The first column is year, second column is ice level. Plot it. I get the blue line. To do a linear curve fit, I choose the basis to be year and 1. Least squares curve fit, so this is the coefficient times year, coefficient times 1. And plot it, and that's what I get. So here's the straight line curve fit for the blue data. With that, I can start answering questions. When is the Arctic going to be ice-free? And from the data, it says the year 2073. Let's do a parabolic curve fit. Again, what a linear curve fit says is I'm assuming the ice melt is at a constant rate. A parabolic curve fit says that the ice is melting at an increasing rate. And that kind of makes sense because as ice melts, you expose more water. More water absorbs more sunlight, melts the ice even faster. So that's kind of a positive feedback loop. That'd be modeled better by a parabolic curve fit. To do that, it's really the same procedure as before. I choose my basis to be year squared, year, and 1. Do my least squares curve fit, and there's the coefficients times year squared, year, and 1. The roots of A, one solution is at the year 2052. About 29 years from now, the Arctic should be ice-free, assuming parabolic curve fit. And here's what the data looks like, the data versus the curve fit. So about 29 years, we can expect the Arctic to be ice-free. Another data set. NASA Goddard's been keeping track of weather since 1880, 139 years of data. Take that data and do a least squares curve fit for the years 1880 to 1930. So kind of same procedure as before. You go to Bison Academy, grab the data set, and here's temperature deviations. In this case, rather than copying all the data, I just want to go 1880 to 1930. There's a couple ways of doing it. That's probably the simplest. So first column is year, second column is temperature deviation. So I'm going to left click, copy up to 1930. Copy and paste that into MATLAB. So there's your data. Start of matrix, paste the data, end of matrix. First column is a year, second column is the temperature deviation, least squares curve fit, and then plot it. Year versus deviation, year versus curve fit. And here's what it looks like. So going between 1880 and 1930, it looked like things were cooling off. Back at the turn of the century, it was thought that we were entering another ice age. And if that trend continued, by the year 2022, we should be down about negative 0.35 degrees Celsius. Well, if we look at the last couple of years, 1980 to 2022, again pulling that data, 1980 to 2022. Pull that data in, I get another curve fit. This will be a parabolic curve fit. Here's what the data looks like. Again, we're certainly not at minus 0.35. We're actually going to be closer to plus 1. I can answer questions like, when is the temperature going to be plus 10 degrees Celsius? And that says in the year 2194, 171 years from now. So that's kind of the homework set. You can curve fit anything. The nice thing about being an engineer is we're really good with numbers. Give me the data, I can analyze it. Plus, you don't have to listen to experts. You can take the data and see what it says for yourself. You don't have to listen to Tucker Carlson. You don't have to listen to Wolfgang Blitzer, anyone like that. You've got access to the data. You've got the tools yourself. What's it mean? Well, that last one says, well, actually all the data sets kind of say that the ice is melting, CO2 levels are going up, temperature's going up. So what? Well, they've actually had models of the Earth and what happens at different temperatures. When there's a 1 degree temperature rise, that'll be the year 2023. We're basically there already. The models predict that you'll have summers like 2003, where the heat waves in France caused 10,000 deaths from become the norm. Flows of rivers like the Po and the Rhine decrease, crop production drops. At plus 2 degrees Celsius, the year 2057, oceans absorb less CO2 because they're too hot. Hot water doesn't absorb CO2 as well. Soils start to release CO2. Vacations to the Mediterranean or Gulf of Mexico in the summer just too darn hot. Start getting crop failures in Africa and Central America, causing mass migrations. Coastal cities flood. A third of species face extinctions. That's something we have to look forward to in about 24 years. 34 years. 3 degrees. At 3 degrees temperature rise, you start getting crop failures in China, and you've got over 1.5 billion people on the move. Collapse of equatorial governments, that's in the year 2082. About 59 years from now. I'm going to live to see that. At least you will, I may not. 4 degrees Celsius. Spain becomes a desert, Mexico becomes a desert, mass migration to northern latitudes, rainforests burn up. 6 degrees. Ice caps are gone, methane hydrates become unstable, raising temperatures in a positive feedback loop. Ocean circulation stops. Hydrogen sulfide producing bacteria flourish, poisoning the air. Ozone layer dissipates, leaving the gland sterilized with UV radiation. Basically, you've got another Permian-like condition. That's in the year 2138, about 110 years from now. That's if we do nothing. This is part of the reason there's a massive push to get away from carbon fuels. You got to get away from coal, oil, fossil fuels. We're running an experiment. This isn't guaranteed this is going to happen, but it has happened before. In the Permian extinction, models predict it'll happen again. Are those models correct? Do we really want to run that experiment? Well, if you don't, you might want to major in something where you can do something about it, like electrical engineering, where you build wind turbines, solar farms, electric vehicles, stuff like that, stuff that can actually have an impact and move away from fossil fuels. That's the future we have looking at. And again, this doesn't depend upon politicians or experts. Look at the data yourself. If it's something you want to avoid, do something about it. That's our job as engineers. So anyway, that's homework set number 3 for ECE 111.